So for this problem, or this warm-up problem in our workbook that Keaton went over, you guys were asked to find if this reaction started with 125 grams of acetic acid and 275 grams of aluminum hydroxide, what's the maximum amount of product aluminum acetate that could be produced? So the first thing you had to realize is that you are given a set amount in grams of each reactant. Kind of like going to the kitchen and saying for pancakes, I have 2 dozen eggs and 6 pounds of flour. Both are required for a pancake, okay? What is the most amount of pancakes, my theoretical yield, I can make given my ingredient amount? And it's like, okay, well, theoretically, if you had 6 pounds of flour and 2 cartons of eggs, you might say to yourself, oh, it's got to be the eggs that determine this, the limiting reactant. I'm going to run out of eggs first. But you don't know that unless you look at the recipe, the set ratio between each reactant. So what do you got to do? You actually cannot trust grams. You basically don't trust grams ever when comparing 2 different substances. You have to say, okay, I got to get to moles. Then using moles, I determine the theoretical yield for each one. And whichever one produces the least amount, that's my actual amount I can make. Because I'm not just going to make a flour pancake that is literally just flour. That's called flour in the shape of a circle. Yes. C2H3O2H. What'd you guys get? Did you guys get 60 grams? Yeah? That was a very sad yeah. Okay, so if you got 60 grams, let's change this then. So it's 60 grams, okay? And the setup is the same though, in terms of you're canceling out your C2H3O2H. You're converting first to moles, and then once you convert to moles, you can use the molar ratio to relate the two to now be in the next compound, which is aluminum acetate. And what would be the new value? It would be 125 times 204.13 divided by 60 times 3. What did we get for that? Sam?
I wasn't here.
Do you have a calculator? Does someone have a calculator present that could do this math? That I don't have a calculator, actually. I love how we're all AP people and none of us have a readily available calculator except for Hayden. Like our motivation. Okay. 142. Is that what you got, Hayden? The best and the brightest are in this room is what I tell myself every day. The best and the brightest.
Wait, which one? We estimated
The whole thing. The whole thing. We are trying to solve this.
I got 142 as well.
Wait, perfect. So then you do it with the second one though, because that's not a safe bet. You can't just do one and be like, yeah, that's it. That's it. That's what I'm gonna get. Because again, it really matters the mole amount that you start with compared to the mole ratio that you have to apply it to, that you have to react it with. So then you do the same process for aluminum hydroxide, and you'd get 720 grams of, oh wow, Kino's old school secretary language. You the little the dashes are old school for bringing it down. Aluminum C2H3O2, 3 of them. Okay, did not know that about Key. Key's just full of surprises, I swear. Okay, so what is our limiting reactant then? Well, our limiting reactant is this, which means, why is this so tiny? What the heckaroonies? Which means that our theoretical, wow, that's a lot bigger, is 142. So, that being said, okay, we now get to part B. How much of the excess reagent? So now we look at, okay, excess reagent wise, that would be this. What we have excess, okay? How much of the excess reagent would be left over? So we know we start with 275, but we need to figure out, well, how much was used? So now we're going to take our theoretical yield, 142, and say, well, how much of the aluminum hydroxide did I actually react to get that amount of limited product? Like, that's it. That's all I can make. There's Otherwise, it's just me left over, right? So then you work backwards and you say, well, dear Lord, what is happening here? You should have gone from 142, okay, aluminum acetate, and then convert it to moles. And then with moles, you can do the molar ratio between the product, okay, one product of aluminum acetate for every one aluminum hydroxide reactant required. And you would have gotten a value of, this needs to be modified because now it's 142. Could someone do 142 divided by 204.13 times 78, please? 54. So we do 54 grams. So we started with 275 and we used up 54 of the grams. So now we have no mental math. 221 grams. Z21, that looks like a false number. Okay. 221 grams left over, excess. Does that make more sense? Feeling good about this? Fabuloso. Okay, so now let's do number 16. Charlie, could you make a note on the workbook that that answer key is botched? It's question number 15, or it's the one I might have, yeah, it's question number 15. It actually might be a different number because I went and fixed something in the workbook. So either way, it's this one under stoichiometry. Just say that the values are different. We have to fix that, unless you want to fix it now. Okay, 16. So I'm given 892 grams of indium oxide. Awesome. It's reacted with an excess of water and forms 10.1 grams of base. What is the percent yield? Write a balanced reaction first. Okay. So indium oxide, where's indium? Indium. How well can I do this on the fly? Iridium, indium. It is a charge of -3. Oh, +3. Indium will take on a charge of +3. So it's going to be indium 2 oxide 3. Okay. Indium oxide is reacted with water. Okay. And forms excess water. So automatically it tells you what's the limiting reactant. If I have excess water. Indium oxide is the limiting reactant. Right there, that word excess matters. It's going to cut down half of your work. Okay. And it forms 10 grams of base. Okay. Okay. So the question is, what is the product? What is the base? That is the question. Okay. It looks like it's going to form some amount of oxide. What is this thing going to form? Indium oxide? Is this going to form indium oxide?
It's already indium oxide, so wouldn't if it says base, then wouldn't
No, sorry, not indium oxide. Sorry, I was thinking hydroxide. Thank you. But I'm trying to figure out, would it be IN2? Wow, this is a weird question.
I think it's INOH3.
INOH3?
You already know from because indium it's the same charge as aluminum.
Yeah. I just am curious.
It's indium hydroxide.
I'm just trying to figure out. Well, we'll leave it. This is is this a hydrolysis of a metal, and it always produces a hydroxide. And I don't think you guys would have known that off the top of your head. Okay. Anyway, moving on. So it forms 10.1 grams. You will know it in the future. You just didn't know it now. And so what we need to figure out is how much, if that's our actual, how much should we have gotten theoretically? And therefore, what is our percent yield? So what you would do is you'd have to balance the reaction, but I think you're not balanced at all. So you need to write the balanced reaction first. So do you have the balanced reaction?
I think I do, but I think my numbers are a little higher.
Okay.
I think I have a multiple, but I haven't tested that. But I have 3 indium oxide and 9 water. We actually form 6 indium hydroxide.
Yeah, that's not it.
Yeah.
Yeah, that's not it at all. But that's okay, because we're just going to take a little cop out right now and just look at the answer key, and it's going to be indium oxide. There's one of them. Okay, so with, I don't know how many waters there are, but I do know, according to the answer key, that there's gonna be two. Honestly, this was a bad question. I'm not gonna lie. This was a bad question. It was too hard because you couldn't even get past the first step without knowing something in the future, but that's okay. So, here's the thing. There we go. This is what we care about. The relationship between the 1 in front and the 2 in front of this. Okay, perfect. Because we already know that all we care about is the indium oxide and the product itself, the hydroxide carrying product. So then let's go ahead and finish out our math. Now it's familiar to you guys. Now it's easy. Okay, so you have 8.92 grams of indium oxide. We got to convert to molar amount. So what's the molar mass of indium oxide?
It's 277.64 grams.
277.64 grams. Okay, that's of indium oxide. And then we go from indium oxide to our product. Okay, and then we go from our product in moles to our product in grams. What's the molar mass of indium hydroxide? Sounds good. Indium hydroxide. What's the molar mass? What do we got? Hydroxide? 165.85 grams, giving us a total amount where we see everything cancel out. Indium oxide, right? All of that's canceled, grams to grams and moles to moles. And what do we get for our final answer? So we get a value of 10.7 grams is what should have been theoretically interesting. That was a mistake. Is what should have been theoretically produced. 10.7 grams. And we need to figure out the percent yield. So what we would say it's equal to actual over the theoretical, which is then equal to 10.1 all over 10.7 times 100, which gives us a value of what? 94.3%. 94.4%. So apologies for the extraneously hard balanced chemical equation, the first step, but the rest of it though should make complete sense. Is there anyone who doesn't understand the math? Forget the balanced chemical equation. Is there anyone who doesn't understand the math? Okay. By the way, head up. It's okay. It's just a pet peeve of mine. By the way, to get 94% yield is like a miracle in synthesis. Like me and my team, we were like 30%, we're doing great. 30%, we're doing hot right there. Well, that was the good stuff, okay? So to get 94, anything above 70% is like pretty impressive. If you can get an 80 to 90% yield in any like synthesis, that's like, especially if it's a newer thing that's like really unfavorable, you're trying to create a mechanism that avoids a mechanism that's unfavorable, that is your miracle worker right there. All right. So there's our warm up. Now let's move on to talking about more special types of reactions. So we are gonna, you guys had a pre-lecture and on acid base, just the first, or actually the second type of special reaction. The first type I have introduced before the lab, known as double displacement precipitation reactions. Now I'm going to introduce a second subcategory of double displacement, but instead of creating a precipitate, we're looking at now between an acid, an H plus carrying proton compound, and a base, an H accepting, okay, proton compound. So the big thing with acid and base is this is the sliver of the tip of the iceberg. Sliver of the tip of the iceberg. Okay, we're going to go with that. This will be its own unit with a lot more math. In fact, the entire unit of acid base is basically math in the coming time. But for right now, we're kind of just introducing it more conceptually and the beginning understanding of how we quantify neutralization. And titration is the laboratory process where we neutralize. So titration is, it's going to be your new favorite lab when we do it. So we have a couple ways that we can quantify from a macroscopic generic scale, which is pH, okay, pH scale. And you guys, if you ever owned a fish or you've ever studied water, or you've ever, like, I don't know, looked at skincare and they talk about the pH of your epidermis, okay, pH is indicative of how acidic or basic something is. And it's not always the most accurate in terms of, it's not the final answer, like, this is how much acid I have, pH of 2. It's like, no, this is how strong my acid is. This is an indicator of how present it is. So we kind of use a series of indicators with acid base. And the pH scale goes from 1 to 14. So however acidic you are, the opposite is true about your basicity, which should total up from a representative perspective to up to 14, which is why we can get this relationship between pOH, the calculation of the presence of hydroxide ions, versus pH, the calculation of the presence or potential of hydronium ions, to be equal to 14 when summed together. Okay, and so I'm not really going to go over the math with you because honestly, this is like third grade math with a button on a calculator. Okay, you plug it in. It's called plug and chug. I give you a value, you figure out what you don't know, you plug it in the calculator and tell me what it is. Okay, but I do want to say that the ability to convert between the two is something that takes more of a recognition skill than an actual math skill. You need to be able to see, given the information on the prompt, that, oh, I'm going to have to work through this relationship to get to pH, or I'm going to have to work through this relationship to ultimately report in pOH, depending on what the question asks you. That's the actual real skill right here. The other thing that I mentioned is memorizing your strong acids versus weak acids and strong bases versus weak bases. I would, for the most part, just pay attention during practice problems. Practice problems will teach you when it's a strong acid and when it's a weak acid, when it's a strong base and when it's a weak base, if you pay attention. If you're just doing the practice problems and you're whipping through the math, you'll learn the math, but it might be a little bit miserable doing some of the MCQ when they assume that you have some of this stuff memorized, all right, for just background knowledge, right? Can anyone tell me what's unique about water? Water, Annalise? Yeah, it can act as a weak acid or a weak base, which is, it's kind of like the Switzerland of acid and bases. Like, it just kind of flips and flops. By the way, Switzerland was not neutral. It totally sold guns like through mafias, but whatever. We'll say it's neutral. History writes it as neutral. It's a lie. It's a farce. But anyway, we'll say it's Switzerland. And what it can do is it can auto-protonate and auto-deprotonate itself. If you put two water molecules in a solution together, okay, they will just donate and undonate to each other. They will donate and accept to each other, okay? And that means there's a net change of nada, okay? And so that means this is why water is the standard for neutrality, pH of 7. This is also why water is often the carrier, the solvent, because it's basically almost inert in the presence of stronger acids or stronger bases. Okay. So now let's talk about titration. So titration is, it is a laboratory, It is a laboratory process. Okay, actually, I'm going to write it in the corner over here. This is a laboratory process, okay, used to neutralize an unknown molarity solution with a known molarity solution. We call a solution that has the known molarity, we call it a standardized solution. Standardized basically tells me I can know it, it's on a table. I can use it for reference, okay? So it's at titration, the titration equivalence point is also known as the neutralization point, okay? AKA the neutralization point when your acid has been completely neutralized or reacted with, neutralized by your base, or vice versa, depending on how you want to look at it. If you want to say my base being neutralized by my acid, fine, that's fine. So the big idea is, quantitatively speaking, this is when your moles of acid present are stoichiometrically equal to your moles of base. So if my chemical reaction tells me I need 2 acids for every 1 base to neutralize, then that's going to affect how many moles of base I need to thoroughly neutralize all the acid. That's why we go off a stoichiometric equivalent. Better? Stoic. Stoic. So what we do is we create a little curve, by the way, that illustrates this process. In lab, the setup would be, this would be called a beret. And this beret goes from 0 down to 50 milliliters usually. It's actually reversed. It's set up reversed because the idea is that we track how much change in volume that we use, and we put our known titrant. This is our standardized solution. Okay, our standardized solution. Oh boy. Okay, in the beret. And what we do is drop by, and I mean drop by drop. You release your base and you see at what point will the indicator solution change color. When the indicator solution changes color, and it usually tends to be a pink. With universal indicators, we tend to look for a pink. There are many types of indicator solutions depending on the type of reaction you're doing with specific compounds. But we, in our labs, will tend to use a pink color. And when it turns, what this tells us is that we have reached equivalence. Okay? The faintest of pink that lasts. So it'll be splashes of pink because initially you drop a concentrated amount of titrant into solution, it's going to spot neutralize. But as you mix it, you realize quickly that you have way more acid still present than you do base, right? So the goal is to have the whole solution become a faint pink, showing the initial crossover of neutralization. Yes?
Is this graph accurate in that it has a vertical slope?
Yes, it is. Because what happens is, as you add titrant, so for our titrant, it would be NaOH in this example, okay? You get small amounts of increasing basicity. And then there's a point, it's almost like magic, when it hits the threshold of everything's been mixed and reacted. And you basically kind of get a zone right at the amount, 50 milliliters for this example, where at 50 milliliters, you are theoretically neutral, pH of 7 for a strong acid, strong base. Okay, for a strong acid, strong base, neutralization equivalence always occurs at pH 7. And then you add more and you jump to a basicity. That's why you see such a vertical nature to it. All right. We often also call the color transition the end point. We can also call it the end point. The reason we have 2 names for it is technically the indicator is its own acid-base reaction inside your acid-base reaction. So technically the color switch is called endpoint, but it is supposed to overlap and align with the equivalence point between your actual acid base that you're studying. It's a time. Unit 8 is going to be a time and a half. Yes.
So I'm still kind of confused about the vertical slope of the graph.
Yep.
Is it just like,
There is no change. First of all, notice there's no change in volume. It's at a particular amount that equivalence is reached. Anything extra, it's too much. Anything less is too little. I often will say in lab that you are a half drop too big. You put a half drop in too much. You remember that?
Yeah, it's really annoying. It's not hardly possible to put in half a drop.
But it is, but it is.
So at the same volume could be a range of pH.
Oh, I see what you're saying. Why is it so long? It's more because to continue the line, you have to connect it.
Okay, so are those dots supposed to be not inclusive? So like if everything less than 2, everything greater than 4? Or
Oh, I see what you're saying. That dot is right before equivalence for number 2, like right before. So it would be at a pH of about 3, and then it suddenly basically jumps to a pH at a 7.
what do the circles represent? Are those drops?
The circles represent points on the graph. Okay. I think I want to tell you right now that we will jump into this later, but there is a point where, let me just put it this way. The lines have to connect somehow. The transition is sudden and quick and it's immediate when it does happen. The only time you get a trackable slope is way before and way after, when you've clearly gotten to an acidic portion and you've clearly gotten to a basic portion. As far as why the line is so long, that is how we draw it in order to make the curve connect.
Also just that it's continuous, it's not discrete because it's like a quantified drop at a time. but then,
Yes.
like, drops can be
It is continuous for the sake of the curve, but it will make a lot more sense when we talk about weak acid, weak base.
So why does it? You may have already explained, but why does it jump so quickly? Wouldn't it like you just keep adding more acid? And it's like, oh, now we're like
Now, but once you've completely neutralized, you now just basic. Like you've reached just this level of extreme basicity, especially with a strong base. The moment you have excess strong base and now what is neutralized, it is defined by that strong base, and that strong base is going to have a pH range of 10 to 12.
So it's the idea that before we had acid,
Mhm.
and now we're putting the base, and they're like canceling each other.
Yep.
And so for like a second, it's perfectly neutral.
Yep. And then
we have
it's-
only base.
Yep.
Okay.
And then it jumps to the next stage. Yes.
Even though, like directly before and directly afterwards, you only have a little bit of acid or only a little bit of base, it's still making the solution.
Acidic or
quite
basic.
quite basic.
Especially because this is a strong acid, strong base example.
Right, I didn't realize they were like canceling.
Yes, they're neutralizing. That is the canceling out. Any other question? Great clarification question, both of you guys. Okay, so that presents us a new math problem. Okay, so this new math problem is 2020 fun. So what we have here is you're going to be asked to calculate the concentration of sulfuric acid, which by the way is a very strong acid. If 32.20 milliliters, all right, of 0.250 molar titrant standardized solution, strong base, sodium hydroxide, is required to neutralize 26.60 milliliters of my unknown concentration of acid. All right, so where in the world are my predetermined calculations? Why did I do this? Oh, I love how I didn't solve it. Great, let's do this. So somebody have a calculator ready to go. So what you would do is you'd first want to write out the balanced chemical equation. And what you're going to notice is that I am a 2-to-1 ratio. Okay, I am a 2-to-1 ratio in acid base. Okay, you are told that you have 0.25 molar 26 milliliters, or sorry, 32 milliliters, 32.2 milliliters of it. So what you need to realize is, well, I need to figure out how many moles of base I have used to neutralize, and that's going to indicate to me how many moles of acid, and therefore I can figure out the molarity of the acid. So that's kind of the order that we're going to go in, from going to figure out moles of base to moles of acid to molarity of acid, again, under neutralized conditions. So we're going to say to ourselves, okay, well, I know that I have used 32.20 milliliters, which I'm going to convert auto to liters just to make my life easier. So 0.03220 liters of base. And it's in a concentration of 0.250 moles per liter molarity of base. And that's going to get me some value of moles of base. And I know that for every 2 moles of base, to neutralize fully, I have to have 1 mole of acid. So that tells me the amount of acid that is being neutralized and therefore present in solution. So could somebody please tell me what that all adds up to in moles of acid? H2SO4. Moles of acid. 0.03220 times 0.250 divided by 2.
0.004.
For what?
0.25.
Okay, moles of H2SO4. Okay, so I figured out my moles of H2SO4. Now, I need to figure out my molarity. Well, what do you need for molarity? Moles per liter. What do I have? Moles. What do I also have? Liters. So I'm going to say, okay, I got this. I'm going to take this is how much of my acid was neutralized, and I know how many moles that were present in that amount of acid, so I can figure out its molarity. So it becomes 0.00403 moles of acid for every 0.02660 liters. And what do I get from my molarity? Some number around 2 something, half something. Probably around 0.45 or 0.52, or what are we around? Molarity wise. Huh? 0.15? Oh. So there's 4 numbers shouted at me at the different rates. 0.015? 0.015. Good. Okay. Aggressive. Okay. Could I get it to the third sig fig? 1.5.
1.2, sorry.
Who said no? What little turd bucket said no? 0.152 molarity of H2SO4. Not too bad. Do the next one on your own. So for this problem, you guys just flipped it. Now we're having the analyte, the solution that we're analyzing, the unknown molarity solution, be our base. And we're titrating known solution, standardized solution with our acid. You okay, Nora? You just like had a hardcore flinch. Okay, got it. I just saw Nora's like shoulder go like 90 degrees in. Okay. So, you would set up pretty similarly, except now you're taking it from the known acid perspective to the unknown base perspective. What did we get for the mole amount of base being neutralized? Moles of base. So then if you have your moles of base and you have your liters amount, okay, you can figure out molarity. So 0.020 moles all over 0.013 liters and 0.0130 liters. And what did you get for the molarity? 0.54 molarity of NaOH. Easy peasy lemon squeezy. Nice work, you guys. Yes. Looks like everything here is 3 sig figs. 40.10, 0.250, and 13.0. Well, I could have written, okay. You would have just written an extra 0. I see what you're saying now. Honestly, let's see, what would the answer key say? Well, this isn't an AP problem. This is a general problem.
How many points do you actually get deducted off?
It totally depends on the problem. not every single problem is counted point for sig figs, but some are, and you have no idea which ones are. Because they ask you to do sig figs for all of them. Yes,
Would I balance the atoms too? Or would I
not the
just-
atoms.
Do I do non-diatomic oxygen?
You would do diatomic because that's the original form it comes in, and then you would do H2O, or which one is it part of? NaO or H2O that you're looking
Or
at?
both?
Yeah, just leave it then.
Okay.
Okay, so sorry, sidetrack. I would say to be safe, this one you should be 3 sig figs because your original data is given in 3. But now I understand your question. Theoretically, your calculator cuts it off if it doesn't see a 0 to be necessary. So it's not your calculator that determines the sig figs. It's you knowing what you started with that does. Are we real? Are we gonna go back to that conversation? Okay. You know what? Technically, they're not. But they represent an important concept. Yes.
Wait, sorry, I just forgot. Is it
3.
because of the decimal?
Because it's a decimal, it's a 0 after a decimal and a non-zero digit.
Okay.
Okay. So let's move on to our final type of special reaction. That's your intro to acid and base. Not too bad, not too bad. It's all stoichiometry, just with a little bit of extra concept. And let's go ahead and talk about redox reactions, which by the way, falls under not a single category. It is its own category. Redox reactions are completely their own category of reaction.
Right, it's like, it's a separate categorization. So you could have a reaction that is a combustion or a synthesis or whatever else, and then, but talking about it in the context of redox is a different way to categorize.
Right. And we're going to assign fake numbers again. Whoop, which means you have a set of new rules to learn and memorize. So, redox reactions, okay? They are a time and a half. They're actually really cool. Okay? Most of the world's reactions I find actually, yeah, most of the world's reactions are redox reactions. Despite the previous type that we've introduced. So they involve their reactions that involve the exchange of electrons between chemical species. And if you're like, that sounds like a double displacement. Technically, double displacements are a type of redox. But combustion can also be a redox, even though none of the molecules technically carry charge. None of the atoms do. None of the species do. Synthesis, okay, decomposition, all of them could be a type of redox. It's its own category, okay? Change of between chemical species. So some examples are over here. FYI, a metathesis reaction is a reaction that doesn't involve electron transfer. So that's just like saying the antithesis. The antithesis of a redox is a metathesis. Okay. So what does redox stand for? Well, it's the combo of 2 words, reduction and oxidation. It's a pairing. Reduction occurs when a species gains electrons.
What's an example of a metathesis reaction?
Certain synthesis reactions are metathesis. I wouldn't know until certain also, certain combustion reactions are also, no, they're all, those are all redox. There are certain synthesis and certain single displacement reactions.
Like if you have a single displacement reaction and switch.
No, I think those would all be redox. Those would all be redox too. No, it might not have no, it would be redox.
Yeah.
It is, I think it's synthesis and decomposition. Certain reactions under those types can be metathesis, but you would not know unless you assigned the oxidation state numbers. You wouldn't know just by looking at it.
Maybe a double displacement with atoms that take on the same charges.
Yes, double displacement might be a great example.
Fluoride, potassium, bromide, double displacement, they would have the same
Charges, so they would stay consistent. Yeah, that might be a great example. You honestly just wouldn't know until you assigned it. You'd have to assign the numbers that I'm gonna teach you how to assign soon. So When we say reduction has occurred, the species has been reduced. Oh my. Okay. And that would be indicated through a decrease in oxidation state, which I will teach you what that means in a second. And it's from reactant to product. Decrease in oxidation state from reactant to product status. Oxidation, on the other hand, is when a species loses electrons. So it has been oxidized. And this is symbolized through an increase, a more positive change in oxidation state from reactant to product. There's a little saying that we like to do, and it says, Leo the lion says grr. Leo the lion says grr for knowing how oxidations and reduction occurred. Leo the lion, lose electrons, oxidation. Grr, gain electrons, reduction. So I'm going to move on up, zoom in. Lose electrons, oxidation. Gain electrons, reduction. Leo the lion says grr. All right. So what are these oxidation states? I'll pause for a second. Yes. Yes, it does. Because oxygen is often an oxidizing agent. But you don't need to know that terminology, but yes, it does. I'm going to tell you not to learn that because the AP asked you specifically not to learn it.
Why is that?
Because it is so confusing. It is the opposite of how all the other terminology references to it. Yes, that is the right face to make, confusion. That's why they are removing it. Sure. It is the reason that your fruit turns brown. It is the reason that copper turns green. It is the reason that rust occurs. Yes. That's what I'm going to teach you. Okay, did I buy everyone enough time? Thank you to your classmates for asking questions and helping with that process. Okay, oxidation numbers are unexamined. Dare I say fake value, okay, to individual atoms in a compound in order to identify if redox has occurred. We love fake numbers. We have a gangster in the room. Are you playing?
Yeah.
Okay, I'll see you up there. Oh, you did? Okay, I'll see you up there. Did you have a question? Oh. Okay, in order to see if a redox has occurred. Okay, so this is super fun because here's your new rules that you have to memorize. No cheers? Oh. So, here's my suggestion. I would memorize only the first few. Everything else kind of just first 5. I'll save you 2. What a deal. It's like when they say BOGO, buy one, get one, you're still paying money, but you're theoretically paying less money by spending money. So same idea. I'm trying to save you guys some. So oxidation rules are best learned by doing them. All right. So let's just do them. Here we go. Quick note, they are written in the same format as formal charge, where you put the sign and then the number. So it looks like formal charge, but formal charge is with Lewis structures. And these are with reactions, but they're written the same. And they have some crossover in the rule assignment, but they mean completely different things. Fabulous. Yes.
How do you know which is which?
Well, are you drawing a Lewis structure here? Okay, that is how you know. Okay. Perfect. So, first problem. Rule number 1, start with the easy win. Any pure element has an oxidation number of 0. So diatomics, oxidation number of 0. So, and I'm going to write this even better. I2, 0. And I don't like that. Well, yeah, I'll do that because there's 2 I's. Okay, and I'm going to write plus 0 because I don't want you to think I'm writing oxygen. Okay, that's the only pure element. I don't see a pure metal in here. I don't see another pure diatomic, so that's all I got. Let's go to the next one. Okay, we are told that the charge of a monoatomic ion is its oxidation state. So for copper sulfate, copper is a 2+ charge. It will have a +2 oxidation state. We still need to figure out sulfur and oxygen because that's not a monoatom ion. That's a polyatomic ion. But we do know potassium. It's a 1+ charge, so it's going to be a +1 oxidation state. Okay, iodine is going to be a -1 oxidation state because it's a 1- charge. Copper over here is going to be a +1 charge because it's a a +1 oxidation state because it's a 1+ charge.
Why is it 2 in the other one?
That's what we're identifying. I think you just identified yourself a redox that has occurred. So,
How do we know if it's 1 there though and 2 there?
well, what does the charge have to be? For iodine, it's always a 1- charge, meaning it's a -1 oxidation state, which means copper must take on a 1+ charge, meaning it's a -1 or +1 oxidation state. Okay, so K2, SO4, KSO. I know that every K has a 1+ charge, so it's become a +1 oxidation state. But there's 2 of them. So the total amount contributed in terms of oxidation state is going to be +2. That's going to matter later. So now that we figured out our monoatomic ions and their oxidation states, which is +2, +1, -1, +1, -1, +0, +1 for each atom of potassium as a product. Now we need to figure out what sulfur is. Well, sulfur and oxygen are in a polyatomic ion that carries an overall charge of 2-. So what we know then is that the oxidation states must sum up to -2 to complement the 2- charge it will carry. So we know one of our rules is that oxygen always is a -2 oxidation state unless it is hydrogen peroxide. In hydrogen peroxide, it's a -1 oxidation state. That's one of your caveat rules. Okay, so we say -2 for oxygen and sulfate, but here's the catch. Catch diddly D. Okay, you have 4 oxygens. So it's like saying you have a contribution of -8 oxidation state from the total 4 oxygens. So that means whatever sulfur's oxidation state is, it must add up to, when added to -8, 2- or -2 to create the overall charge that polyatomic carries. So sulfur must be +6. That is not a real charge for sulfur. That is the fake charge that we assign it that aligns with our known real charges for that polyatomic. So,
hold on. So we assign a random charge for
it is never random.
An arbitrary charge
that aligns with a real charge.
That aligns with the real charge, but based off of oxygen. Why are we multiplying sulfur by 2?
Because how many sulfurs are there in the polyatomic?
In the polyatomic, 1.
Okay, that's all you need to know. There's your answer.
Okay.
Yes.
But there's 2 of them. We multiply.
Yeah, why don't we count the coefficients?
Because the coefficients don't matter yet.
Okay, then all right.
It's the same
I
as
have
ours.
2 questions.
So to equalize it, we're making sulfur B6.
To not equalize it, to get the oxidation state to sum up to the real charge, 2-. that would be equivalent to a -2 oxidation state over the polyatomic itself.
To make
What?
it good with copper.
So,
Overall, sulfur.
so hold on, guys. Am I Maleficent and I am a wicked witch for teaching you this? Your charge must always, if you have a charge present, it must be matched by your oxidation state. But here's the catch. If you have a charge present, it must be matched by your accompanying oxidation state. But if you're dealing with polyatomics, you have a group of atoms carrying that charge, which means the group of atoms oxidation state must be equal or match the charge.
So what's the charge in this case?
Sulfate, SO4, 2-.
You can also do
It's 2, but wouldn't the copper change the charge?
But the copper changes charge through the reaction. What we see here is copper goes from +2 to plus charge, oxidation state of +2, to what you immediately notice. Our known reaction produces copper iodide, which is now requiring copper to take on a +1+ charge, which would be a +1 oxidation state.
So we change the charge of the transition metal.
Not always, but in this case, yes. It is dependent on the given always provided reaction. Yes. Okay, so
Okay, so copper and the reactant side is +2 because SO4,
is a 2-, and you only needed one of those polyatomics.
the compound needs to be 0.
Yes, because that's good compound making with the actual charge rules.
Okay, and then for the SO4, we assigned sulfur based off of oxygen because oxygen is always -2
Unless it's hydrogen peroxide or OF2-. It's one of the caveats.
And then one more question. I think I forgot. what it was.
Perfect. That's a good thing. Yes.
Do oxidation states matter beyond identifying whether something is a redox reaction?
No.
How do we know?
Until we might want to quantify based off of electron transfer. So we can do stoichiometry with this as well, but we're not there yet. That's coming.
How do we know to give sulfur the fake charge?
Because oxygen is part of the rules, a guarantee.
Yeah, but
Because
iodine-
oxygen is a
iodine and
guarantee.
Potassium aren't.
But so the iodine that you have.
What do you mean potassium is? It's always a +1. Yes?
I don't understand why sulfur is.
Because when you look at sulfate, the charge must be 2-. Sulfur plus 4 oxygens must be 2-, which means the oxidation state of those 5 atoms combined must be. Exactly. There we go. Very nice. I'm going to move on because I have to. So the same thing would be true here. The same thing would be true here for the sulfate on the other side. It's a conserved polyatomic. So we're going to see that the oxygen is going to be -2 plus 6 times 4 -8. When added together gives us the 2- because the polyatomic charge is conserved because the unit is conserved, which means the oxidation states will also be conserved. Now we look, now we look at our oxidation states for each individual atom. And we say from product to reactant, what changed? And we see, well, copper changed from +2 to +1. Sulfur does not change. Oxygen does not change. Potassium does not change, but iodine changes in one particular compound. It starts off being one source of iodine, but it splits up into 2 sources of iodine. And the second source, the pure diatomic iodine, is what is the changing iodine oxidation state. So it's this iodine with that iodine changing. So it is technically one form of iodine undergoing a change in electron transfer. Yes.
Why is potassium iodide called iodine?
Potassium iodide, it does, Ki. That's not an L.
No, he's talking
No,
about
in
the
the
last.
product side.
He's talking about.
Oh,
That's a
because
typo, that should say
someone-
potassium sulfate.
Someone made a dum-dum that was not us, but another person that I stole this image off the internet from. Okay, perfect. Copyright. I think I gave source somewhere. I think it might be hyperlinked in the docs. Who knows?
When you're allowed to do that, that may not be.
Oh, I did give source. Images from Advantage. You're welcome. So what we would say then is
It's like images I saw from the website.
oxidize. Leo the lion says, Gur, if I lost electrons, I am oxidized, which means I'm more positive from reacting to product. So I am oxidized iodine. I go from a -1 to a +0. But reduced wise, I am copper going from a +2 to a lesser number, +1. All right, why don't you try the next one on your own? And you get 2 minutes. Keep going. So for this one. Okay, easy win. Chlorine is a +0. It's a pure element. Sulfur is a pure element, +0. Hydrogen sulfide. Each hydrogen takes on a +1. Okay, because hydrogen is always a 1+ charge in the diatomic, but I have 2 of them. Okay, so something to keep in mind is that what must sulfur be to cancel it out? Sulfur must be a -2. Now I look over here. H is a +1. Chlorine is a -1. So what do I see as being transformed? I see chlorine going from positive to negative. Sulfur going from negative to positive. So what is oxidized? I would say oxidized. Leo the lion says, Gur, lose electrons, sulfur. Reduced, okay, chlorine. Moving on. How would we? Okay. We got 2 minutes to go through the next page. Let's go. So how do we write redox half reactions? This shows us the transfer between electrons for reduction part and oxidation part. At this point, I would listen. Okay, listen to me. So what we see here is reduction wise. Copper goes from, this is an oxidation state of +0. Copper is reduced, cobalt goes from cobalt 3+ to cobalt 2+, which means I have lost 1 electron. So my redox half reaction for the reduction portion would be cobalt 3+ going to cobalt 2+ and 1 electron. Okay. Oxidation wise, what I see is nickel goes from 0 to 2+. I've lost electrons that become more positive. So nickel goes from +0. Okay.
Hang on.
Hold on.
Reduction gains an electron. Cobalt 3+ plus an electron.
Good God. Okay, sorry guys, I'm trying to move too fast myself. Gained. Okay, so cobalt 3+ gains 1 electron, and then it becomes cobalt 2+. Stay right where you are. I swear I will finish this. Nickel, okay, goes from nickel 0 to nickel 2+. Hold in there, kids. Okay, nickel 0 to nickel 2+. So that's like saying I have lost 2 electrons as a product to now be nickel 2+ and 2 electrons. Okay, if you were to balance them, what you would have to say is that the amount gained is the amount lost. So you'd multiply this by 2. So it would become 2 cobalt, okay, plus nickel, 0, okay, goes to 2 cobalt, 2+ nickel, 2+. And you can do the practice problem here. It's more challenging on your own. Okay. Okay, guys, sorry for the rush nature in class about finishing up half reactions and redox. Let's go through one more complicated one, and let me kind of go a little slower for you guys. I do apologize for the time. Okay, so we would assign oxidation state. So what we would see here is carbon and oxygen in the carbon dioxide. Oxygen would be a -2. And since there's 2 of them, it would equal up to a total sum of -4 oxidation state. which means that your carbon in CO2 has to be a +4. Okay, what about your H2O? H is always a +1. And since there's 2 of them, you know that it's going to be contributing a total sum of +2. And your oxygen is always going to be a -2, unless, of course, it's hydrogen peroxide or oxygen in OF2. Okay. So those are your oxidation states for your reactants. Now let's look at your product. We have C, H, and O all combined, and pure diatomic oxygen, which is going to be +0 because it's a pure element. Now let's look at oxygen. So we have -2, okay, times 6 of them. So you're going to have a value of, okay, a -12 that you're going to have to even out with the H's. You know that you have 12 H's, okay? So, and this is a set value. So you get +12, which means, haha, funny thing about your carbons is that your carbons would actually, as a result, we would say they'd have a 0 oxidation state. This is a very rare example, but what you would see is in order to keep everything neutral, because it's a neutral molecular compound, you would have to have a +0 times 6 evenly 0. I am so sorry. This is a very difficult example, but one it's worth looking at. So then you look at the oxidation states and you say to yourself, okay, well, let's look what's changed. Oxygen has gone from 0 or from -2 in both of these to a +0. And then it's also one form of oxygen has stayed -2. Okay, so you know that one subsect of oxygen is changing. You look at hydrogen, it stays +1. You look at carbon, and it goes from +4 to +0. So we would say then that our reduction, gain electrons, is carbon, oh no, oh boy. Carbon +4 gains 4 electrons to become carbon +0. I realize it's crazy. So oxidation-wise, lose electrons, become more positive in the oxidation state number, is oxygen goes from -2 and it becomes oxygen +0 and 2 electrons. Now, to write the balance sum reaction, sum redox, to put each half reaction into one full reaction, we need to electronically balance. Whatever electrons we gain, we must also lose. So what we see here is we're going to multiply everything by 2, and we get that our sum of reaction is C +4, reactant side, O -2, 2 of them on the reactant side. Okay. And it goes to form C +0 and 2 oxygens with a +0, which theoretically, if you want to write it super correctly, would be oxygen 2 because it's pure element oxygen, therefore conserving also the amount of atoms. So that is how we would do it. Your quiz tomorrow will expect you to be able to assign oxidation states, including those involving a polyatomic, where you have to do the sum of the oxidation states, and write half reactions. And you do not have to electronically balance. You just have to write the individual half reactions, where you track the electrons being transferred for a respective atom in a chemical species. All right, guys, really good luck. I know this is moving really fast, but I'm very proud of you. And congrats. Yay. Good attitudes.